In this video, I will go over the homework that follows the lecture 8.1, in which we introduced a new integration technique called integration by parts. As always, I hope you watch this lecture, as I will be expecting you to be familiar with some of the concepts and material as I'm doing the homework. I may refer to them. So let's go ahead and jump right into the homework. And in problem number 1, we have an integral in which we are not given a choice of the integration technique, but we told to use integration by parts. And when integration by parts is done, I suggest you to announce it by creating a space in which you will be doing all the integration by parts related work. And part of such work is introducing two functions u and v. And in this case, again, we're not choosing anything. We are given these choices. And as you chose, or as you were given the u and dv, the next step is pretty straightforward. You have to identify your du by differentiating your u. So it's going to be negative 5 dx. And we're going to find v by integrating your dv, which may take an additional effort. So that's why it's really important for you to choose your dv in such a way that you know how to find v. And in this case, you can pause and just work it out yourself, but the antiderivative of cosine of 2x is just 1/2 sine of 2x plus c, but for the indefinite integral, it doesn't matter what the value of c is. So if it doesn't matter, then we can choose it to be equal to 0. And now that we've done all the preliminary work, now we can put it all together using this formula. And the formula, I'll just put it here. The integral of u dv is equal to uv minus integral of v du. And this is kind of what's in our mind as we're putting it all together. Here we have our u dv, and now what I'm about to write, it's uv. So here's my u, here's my v, and minus integral of v, which is 1/2 sine of 2x, du, which is negative 5, and dx is now part of this new integral. And the whole idea is that we want the new integral to be simpler than the original integral. And here, after we do all this basic integral hygiene, that is, take out all the constants, we see that the integral of sine of 2x is much easier than the original integral. So the final answer is, and not much going on the left side, right? Once you got something out of the integral, it's pretty much just copying it over and over again. But here we have 5/2, and now the antiderivative of this is going to be negative 1/2 cosine of 2x. And here, if you don't see how to go from here to here, I'm not going to show you every single step, because at this point this is considered to be basic. So I'm just going to give you a hint. To go from here to here, you have to do a substitution, linear substitution, t equals 2x, and it will get you this result. So that's the answer. Now we're going to enter it. So negative 5/2. Let's try again. Negative 5/2 x sine of 2x minus 5/4 cosine of 2x plus c. And you may see other people write this differently. I'm used to writing it, arranging it vertically, like here's my u, here's my du, here's my dv, here's my v. Sometimes you see people arrange it horizontally, so here's u, here's du, here's dv, here's v. So it really just a matter of preference. Let's continue. This is a very similar problem in the sense that we have a product of two functions of different types. So in the previous we had x linear and trigonometric, or polynomial and trigonometric, or rather rational and trigonometric, and here we have rational function and exponential. So here the choice is of u and dv. It's not up to us again, so we're just gonna follow this choice. But the idea is simple. Once that choice was made, the next few steps are pretty straightforward. So it's just a matter of you integrating and differentiating your whatever you chose to be your u and dv. Here, again, I'm not gonna do all the work here, but if you grab a piece of paper and do substitution, t equals negative 4x, you'll see how it works out this way. So now we're going to put it all together. It's u v minus v integral of v du, and we ended up with a much simpler integral. So let me take out all the constants, simplify a little bit. And this integral is much simpler, so to do it, all we have to do is just a basic substitution. Again, if you don't see it, then here's my hint. I'm not going to do every single step, but if you do this substitution, t equals negative 4x, you'll be able to obtain this result. Now, someone may ask, why don't we distribute the negative 5/4 to the plus c? That doesn't matter. You can distribute the negative 5/4 to plus c, but constant is a constant, so it doesn't matter if it has 5/4 there or if it doesn't, it's still just a constant. So let's type the answer. I'm simplifying it as I'm typing it, just because you do always want to simplify before you, if it's an intermediate step, you want to simplify before you continue to the next step. You don't want to perform integrations on non-simplified expressions or functions that are expressed using non-simplified expressions. Here's the next problem. This time they're not giving us a choice, so we have to make the choice. And this is a standard problem, and what you want to see here is the that invisible 1. So here we have times 1, and again, it's being a standard problem, it's a standard solution. This is going to be my u, this is going to be my dv, and I'm going to announce integration by parts. I'm going to announce my choice of u. My u is arctan of 4x. My dv is 1 dx. And du is going to be 4 divided by 1 plus 4x squared. So this is just the chain rule. So you can check, you can pause the video and carefully work this out. And v is an integral of 1 dx, which is just x. So this is my setup. Now I'm going to plug everything in. So here's my uv. So we're going to have x times arctan of 4x minus integral of v du. So here's my v, here's my du. And we're going to simplify it. There's nothing you can do with this x arctan of 4x. But here, I'm going to clean this up. So I'm going to take this 4 out. I'm going to put x over here. I'm going to distribute this over. Apply the power to 4 and x. And the question is now, how are we going to do this integral? And this is a... Well, first of all, it's a much easier integral because at least we know how to do this one. That's the first thing. Now, how do we do this one? The answer is by substitution. And what substitution? So let's set up substitution. So I'm going to substitution. So here's my substitution. I'm going to take my entire denominator and let it be t. Then dt will be equal to 32x dx, meaning that x dx, which is part of this pattern here, is equal to 1 over 32 dt. So I'm going to, and now you have to make a decision how you want to organize your solution. Do you want to kind of hit the pause on this one? Like hit the pause button, right? And just focus on this integral. You can do that. So let's focus on just this integral, the one I underscored. We have now an integral of which is x dx, it's 1 over 32 dt, but in the denominator we just have t. So it's a very simple problem. It's just 1 over 32 integral of 1 over t dt, which is 1 over 32 ln absolute value of t plus c. But let me actually move this over. So organizing your work is really, really important now more than ever. And we're replacing back the t for what it stands for, gives us this. So remember, this is just this part right here, right? So we haven't done anything but this. So now we're gonna unpause our solution. So we're gonna hit the play button here, and we're gonna continue writing the answer to the original problem. Don't forget that this 4 wasn't part of our intermediate result here, so we put 4 over here, and now I'm going to write the answer for the integral. So it's going to be 1 over 32 ln of 1 plus 16x squared plus c. So this is my final answer, and I'll simplify it as I enter the answer, but pretty much we're almost done. 4 over 32, it's 1 over 8. Here we have ln, but because 1 plus 16x squared is always positive, you don't really need the absolute value here, but I'm still going to keep it there, because it's not wrong to have it there. And it's better have it when you don't need it, rather than not have it when you need it. And this should be the correct solution. So again, the focus here is on organizing your work. And you can see in this solution, they decided to keep 4 as a part of the integral, which was their decision. We choose not to. The final answer is the same. Alright, so let's move on to the next problem. So this was question number 3, and now we're moving on to question number 4. Here we have we have a non-trivial integral, so it may seem like you can do it with substitution, but the pattern is just not there. So I don't think there is an obvious substitution that will work here. So we're going to try to do it by parts, and to do it by parts we need to choose u and v. And I'm going to choose my u to be ln of 5x to the power 5. And my dv, it's what's left, right? So again, my choice was very strategic. I choose my u to be something that is easy to differentiate, but we can differentiate any function. The main idea here was on kind of making sure that dv is not hard for us so that we don't know how to find v. And in this case, finding v should be pretty straightforward. So du is derivative of ln is 1 over, so it's the reciprocal of the input times the derivative of the what's inside. And it looks like this can be simplified a lot. So it's going to be 5 over x dx, which is nice, right? So this is my du. And my v is an integral of 1 over square root of x dx, which, if you notice, if I just throw 2 over here and 2 over here, it just becomes 2 square root of x, which is nice. So now we're going to put it all together. So let me separate this. So we're going to do uv, so ln of 5x to the 5 times 2 square root of x minus integral of v du, and after simplifying it, so let me rearrange this. After simplifying and taking out the coefficient and reducing the powers, we have this. Same as before, if you just notice that pattern, you can throw an extra 2 over here, an extra 2 over here to see the pattern. So it now became a very trivial integral. So it's 20 square root of x plus c. So 2 square root of x ln of 5x to the power 5 minus 20 square root of x plus c. Let's see if we got this right. Yeah, we got this right. So let's go to the next problem. Problem number 5. Very similar problem, right? So meaning that we don't need to reinvent the wheel here, especially with that little hint. The hint pretty much tells us what we already knew based on our experience with the previous problem. The u is ln, dv is 2 over x to the 4. However, if it was up to me, I would just take that 2 out of the integration process and not worry about it. Here we have 8x divided by 4x squared, which can be simplified as 2 over x dx. And here, to find v, we have to integrate. And it doesn't help me to write it that way, so I'm going to write it as an exponential form. So v, and I'm going to rearrange things because we're going to need that extra space anyway. Can't seem to grab that thing, but okay. So it's this one here, and this one's gonna be this one here. So we have 2 x to the power -3 divided by -3 plus c, right? But we don't need that plus c, so we're not gonna write that. Simplifying it, we get -2/3 x to the -3, or -2 over x to the power 3x cubed. So I guess we have to pick which one we like more, and let's just stick with this one. So this is my integration by parts setup. Now that we got it out of the way, we can maybe minimize it a little so it doesn't take a huge chunk of my page. And now we're going to continue with the solution. So it's going to be u v minus integral of v du. And here we can do some basic maintenance, like, you know, simplify, maybe just a little. Take out all the constants. And now we have what, x to the power 4 in the denominator, so it's just x to the power -4. And again, sometimes it makes sense to just hit the pause here and just, you know, do this integral separately on a, maybe even on a different piece of paper, and then kind of unpause your solution and write the answer. But in this case, this integral is simple enough that we can just continue writing out the solution. So the answer is plus 4/3, and here we have x to the -3 over -3 plus c. So let's type the answer. It's going to be -2 ln of 4x to the power 2 divided by 3x cubed minus 4 over 9x to the power 3. Let's check. And it's all good. So this was problem number 5. And we're moving on to number 6. Integral of 4x e to the -5x dx. I personally would take the 4 out so it doesn't interfere with the solution. We don't need to have too many constants. And now we're gonna do integration by parts. I didn't see that. They actually suggested us, so we don't get to choose what to do here. We are told what to do. So if u is equal to 4x and dv is equal to e to the negative 5x dx, then du is equal to 4 dx, and v is equal to integral of e to the negative 5x dx. And again, it's a simple integral, simple linear substitution, and here's the answer. If you need help, I would suggest you to pause this and just do this integral by hand. But here's the hint. It's just a substitution, t equals negative 5x, and it just gives you this result. So this is my integration by parts setup, and now I continue with my solution here. So I write uv 4x times negative 1/5 e to the negative 5x minus integral of v, which is negative 1/5 e to the negative 5x du, which is 4 dx. Again, basic maintenance. We have negative 4/5 x e to the negative 5x plus 4/5 integral e to the negative 5x dx. But if you're paying attention, you notice that it's exactly the same integral as the one which is did above. So the answer will be, again, negative 1/5 e to the negative 5x plus c. So that's my final answer. And I'm going to type this up. And you can simplify it in probably more than one way, but I consider what I entered to be simplified. Someone may have a different opinion, but it's the same functions, just written in more than one different ways. All right, so next problem. We have integral of 5x secant squared x dx, and here we're not told what to do, so we have to make the decision ourselves. And what helps us to make the decision here is, well, first of all, I'm going to take that 5 out now that I can make my own decisions, and let me just rewrite it then to make it look prettier. Is the fact that whatever your u is, it has to be easy to differentiate, which is never an issue. But what's left after you choose your u has to be such function that is easy to integrate. And here we notice how this is a perfect split. X is easy to differentiate, and we also happen to know the antiderivative of secant squared x, which is... you can pause the video and ask yourself what is it, but I think it's tangent x. So this is my integration by parts setup. So I'm going to continue with my solution. I still have that 5. And now what I'm writing here is it's just an integral. So we're going to have like this parenthesis here for the entire integral, right? 5 is not part of it. 5 is outside. And we're going to write uv, which is x tangent x, minus integral of v, which is tangent x dx. And this could be the reason why you may want to keep 5 inside and make it part of the integration by parts so that you don't have to deal with this giant parenthesis here. But here's what we have, right? We have 5 that applies to the entire integral, and inside we have x tan x minus integral of tangent x. The integral of tangent x is just, let's see if I remember it correctly, but it's a table integral, so it's just the ln of, so it's going to be plus over here, but it's ln of cosine of x plus c. And if you want to do this by hand, the way we go from here to here, it's by rewriting tangent as a sine over cosine and doing the substitution t equals cosine x. So this is what I think the answer is. 5 applies to both, so you can write 5 here or rewrite it separately. So it's just a matter of preference. All right, let's type this up. All right. Another problem. And we have to make a choice ourselves. So we're going to announce integration by parts. And now it's really important for you not to get confused between integration by parts and substitution. Sometimes there are substitution problems that have the similar pattern, but in this case, there's just no pattern for substitution. So we're going to do integration by parts. Actually, we may not want to do integration by parts. So now I'm looking at this. If we were to do it by doing integration by parts, we wouldn't get anywhere here. So this is actually the time when we have to learn how to combine integration by parts and substitution. And the first thing we want to notice here is substitution, actually. So we're going to do substitution. So my substitution is going to be, and again, you may ask, how do you know that? It's usually just by poking around. If you try integration by parts right away here, you're not going to get anywhere. As I start writing it, I kind of realized that probably not going anywhere with that, which led me to the thought of substitution. Now, substitution is always an option. And here we're going to make the exponent my new variable. We're going to find dt as 12x cubed dx, and that means dx is 1 over 12x cubed dt. But also let's not forget that, because I kind of see the pattern here, so x to the 4 will be same as t over 3, right? So that's all part of the substitution. Now, let's continue here. We now have integral of x to the 7 e to the t. Instead of dx, I'm going to write 1 over 12x cubed dt. Now, pay attention here. 1/12 goes outside. X cubed and x to the 7 cancel, so this becomes x to the 4 et dt, but x to the 4 is t over 3, so here's the final answer. And now 1/3 goes outside, so it's now 1 over 36, integral of t e to the t dt. And this is our new problem. And you have to admit that this problem is much easier than the original problem. So let's make this our new problem. We're only going to focus on this integral. So 1/36 is not part of it. And we're going to do this integral by parts. So my u is t, my du is dt, my dv is e to the t dt, and my v is the integral of e to the t dt, which is e to the t. So notice how if we choose, as many books like to call it, u substitution, so we're putting a pause here for right now. If you choose u to be your variable of substitution, then you would end up here with some nonsense. U is u, du is du, and dv is e to the u. So that's why I always recommend using t as a variable of substitution. And let's continue, right? So we have uv, so we have t e to the power t minus integral of v du, which is actually pretty straightforward now. Now remember, this is just that integral. So now we're gonna hit the play button here and continue with the solution. So we still have like 1 over 36 over there, and it's going to be 1 over 36 t e to the t minus e to the t. And remember that plus c, we can just always stick it at the end. You can distribute 1 over 36 to c, but it's just not necessary because it's still going to be a constant. And the last thing we have to do here is we have to acknowledge that t is not the original variable. X was the original variable. So instead of t, we're going to write 3x to the power 4. So this is going to be 3x to the power 4 e to the power 3x to the power 4 minus e to the power 3x to the power 4. So I guess we have parentheses here, plus c. And we can totally try and factor out e to the power 3x to the power 4 over 36. And we have 3x to the power 4 minus 1 plus c. So this is the final answer. So let's type it up. We have e to the power 3x to the power 4 times 3x to the power 4 minus 1, and all that divided by 36, and we have plus c. So this was problem number 8. And we finished the homework that covers integration by parts. I was hoping for more problems, but hopefully you'll get more problems. And if you have any questions, feel free to reach out.